So do you suggest that I like set up a different appointment with you?
No, I don't do personal questions.
Well,
Anything I say to one student, I should be able to say to any student. So,
well, it's not so much like personal, like not really related to physics, but it's just like a conflict that I was like wanting to talk to you about.
I don't do personal consultations in any form. If you have a question, you should post it on Piazza. You can do it anonymously, and I will answer it to the best of my abilities.
Okay. Alright, so I don't mind doing it on Zoom, but I guess really, so for the second midterm, I may have a conflict and it's not guaranteed yet, but it's something that I don't have any control over and I won't know until closer to the date. But like I'm genuinely concerned that I won't be able to take the midterm at its scheduled time. And I was wondering if it would be possible for me to take it earlier or later in the day, or just talk to you about it as the date gets closer, or like ask my TA if he would be willing to proctor me at a separate time.
It's not about TA, it's not about proctoring, because these exams all take place online, and because all exams will be in electronic format, there will no way to secure the content of the exam if it's taken on another day, another time. That's impossible. That's why in this situation there is no option. If it would have been a different format, usually it would be possible to give a student a paper exam and proctor it, but in this situation it's just physically impossible to make sure. And no matter if someone gives any promises, I cannot rely on promises. I only can rely on a concrete specific situations.
Mhm.
So I strongly recommend not doing that.
Well, no, I mean, like, obviously my first choice is, like, not missing it. Like, I'd rather take it when it's scheduled. But it was just, like, a backup plan because I don't know if I will have the conflict or not. Like, it's not in my control.
Well, there are certain issues, elements, features which may be out of our control. And if that is out of your control, making up exams is out of my control.
Mm-hmm.
You need to know for sure, and you need to make your mind.
Well, I just don't know what to do. Like, what do you suggest I do?
Well, if you can't take an exam, you have to drop this class.
I can't. I paid $3,000 for the course, and I do like the course. Like, I don't want the one conflict to be the reason I don't take the course. Like, I've had.
How much did you pay for this? How much did you pay for the course?
$3,100.
They raised the price. I didn't know that.
Mm-hmm. And like, I've had other professors in physics, and you're honestly like the best one. But even though it's remote, like you taught me more 105 material than my actual 105 physics professor. And I was really
I need to discuss this with my superior. I cannot make a decision.
Okay, that's fine.
So I can do that, and you will have to let me know as soon as possible your situation.
Mm-hmm.
I can promise you that I will have that discussion, and what they say, that I cannot promise you. Okay? Mm-hmm. If they say fine, I'll do it. I will find a way. Mm-hmm. Okay?
Yeah, thank you so much.
All right. Next question.
Okay, so.
And I need to, just in case, send the link because I know that some students don't remember that it's always the same link. So I just want to post it on Piazza. And just a second. What do I want to do? I want to know on this. Powers now. Zoom link. By the way, can you see a screen or it's fuzzy?
It's a little fuzzy.
Yeah. If it's fuzzy, you need to tell me. I can fix it. Oh. All right. One more thing. I need to open up WebAssign, just in case. Is the screen better now?
Yeah, I think it's clear. I think it's just zoomed out.
It sometimes it comes out of focus, and when I know, I can just go. All right. Oh. Let's talk physics. Please ask a question.
So my first question is regarding the electroscope. So I understand what the charges would look like on an electroscope if you do it through induction or if you physically have like rubbing.
Yeah.
If I just bring a conductor in contact with an electroscope and then move it completely away, would the charges on that base be whatever charges I transferred over, or would the entire electroscope have the same charges throughout?
You assume that you're bringing a charged conductor.
Mm-hmm.
Positive or negative? Choose one. Negative. So it has extra electrons. And if you now touch, some of these electrons will run onto electroscope because they will have some room and they repel each other. And when you then remove this connection, some of those extra electrons will remain on the electroscope and it will remain charged.
Mm-hmm.
That's it.
Okay, so that would be the same thing as rubbing the
Yes.
Okay.
See, if it's the conductor, electrons, even if you just touch, electrons can run easily. But if it's insulator, in that case, you kind of need to move scratch them off, move them back and forth a little bit.
Okay, I see. So if it just touched it and it was an insulator, that top plate would have positive charges.
Well, basically, no. If it would have been an insulator and you just touch it, some very, very small amount of electrons might be moved one way or another, but it would be so small amount that it wouldn't make any difference. Basically, we would not see any deflection.
Okay.
Okay.
Yes.
Next question.
Okay. So for insulators, they can be polarized and they can charge through induction. It would just happen over a long time, right? Like they would need a lot of time and energy to do that, right?
Well, if you have an insulator and if you just bring another charged insulator and touch or even scratch, it doesn't make much difference. It might make a little bit of difference in this location, but that's it. If you want to make some difference, you have to apply a strong electric field, relatively strong electric field. And this electric field polarizes molecules inside. Each molecule becomes like an oval in shape, because electrons an electron is negatively charged, so force acting on each electron will point opposite to electric field. So it kind of moves electrons a little bit away from a positive nucleus.
Oh, so the only way to polarize an insulator is to apply a strong electric field to cause the charges to separate.
Move away from each other a little bit. Yes, it is a separation, but it is not like a separation in a conductor. These electrons, they cannot run away. They still stick to the same nucleus. they just shifted a little bit away in one direction, the symmetry is broken, and now this becomes a dipole.
Okay.
But this dipole is not an actual physical dipole with two charges and a stick. There is no stick. If you remove electric field, they become back, you know. So this dipole was neutral and remains neutral. But when it's slightly kind of elongated, like an oval, now this polarization creates its own electric field, because what you do, basically, you're now observing a lot of these dipoles inside. Each has minus, plus, minus, plus, minus, plus, minus, plus. So each has an electron shifted away from a nucleus, and that makes like a layer, negatively charged layer, and a positively charged layer. Well, but you have similar dipoles all the way through the dielectric. So these, which are close to each other, they basically neutralize each other. And what you have in the end, just certain surface charge on one side and some surface charge on another side. And these two layers now generate their own induced electric field.
Okay. So can you charge an insulator through induction?
No. Charging by induction involves a step when you touch it to remove, let's say, extra electrons. But for that, it has to be a conductor. If you touch an insulator, it doesn't make any difference practically.
Okay. So when we were talking about discharging objects, we always talked about using conductors to discharge an object. Can you theoretically use an insulator to discharge an object?
Theoretically, yeah, but it would be much harder to do. Because you remember an experiment with a fur and a plastic bat. The mechanical interaction has led to electrons moved from piece of fur on a bat. Theoretically, some mechanical interaction make those electrons move back. It's just harder to do.
Okay. And then going back to conductors that are charged by induction, can you actually move a charge like an electron over space from the object to the conductor, or do we only talk about induction when there's like a conducting wire going to the ground?
Over space, you mean like through air?
Yeah.
Not in real conditions. It has to be something really, really strong.
Okay.
If you would be adding, using a very powerful power source, for example, you would be adding more and more and more electrons. Eventually, you would have so many electrons, they would repel themselves so strongly that some electrons would start jumping away. But that's unrealistic under regular circumstances.
Okay. And then my next question goes to the dipole that we put in an electric field. And we said that when friction exists, then the electric field is not zero, but that eventually...
No, we didn't say that. You're making different statements. So when we have an electric field acting on a dipole, on an actual dipole, a stick with two charges, I think this was the situation. What I said is, if you had like a hanger or pivot here with friction, eventually this dipole would stop in a certain configuration. And what would be that configuration?
It would be parallel to the electric field.
Yeah, but there are two options, like this or like this. One is stable, one is unstable. So unstable is very unlikely. And which of these two configurations is stable? That's the question.
First one?
the first one. So let's see what's going to happen if it's a little bit off.
Oh, sorry, I meant the second one, right? Because the second one, the electric field points towards the negative charge.
The second one. Well, again, technically what you should do is to imagine what's going to happen if this system is slightly, just a little bit, not in equilibrium, deflected from equilibrium. And in this case, we know what should happen. Here we should have a force acting like this and a force acting like this. So it actually will make this dipole move more and more away from equilibrium. But here, the force will act like this. So it actually will make dipole move back to the equilibrium. So this is stable, you're correct, stable equilibrium, and this is unstable. So this will be the final orientation of this dipole. But if friction is 0, in that case, it would have to move forever, but it cannot spin. It can just rotate constantly, because when a negative charge will be below this line, in that case, this force wants to bring it back. So in that case, with no friction, it would have been just oscillating back and forth, back and forth.
So my question comes from the stable configuration. Why is it that the charge cannot be, like the configuration has to be parallel to the field and it can't be perpendicular to the field?
Well, I would like to see your picture. You have to draw a picture. Your picture has to show electric field lines. Your picture has to show the dipole in the orientation of your choice. So, well, I know the stick. You want to be perpendicular.
Mm-hmm.
Which do you want to be positive? Which do you want to be negative?
Top positive, bottom negative.
All right. Now you have
force vector.
Well, you have to draw force. You have to draw force on each acting on each charge. So on a positive charge, how does it point? How does the force point?
Downwards towards the negative charge. Or actually, no. If we're looking at each one separately, then for the positive charge, the force vector will point towards the right.
Well, technically, you're kind of right, because you should have asked the force acting on what from what. I'm not asking for a force acting from a negative charge on a positive charge. I'm asking, as you're right, for the force acting on a positive charge from electric field. And how does the force acting on a negative charge from electric field point?
Towards the left, opposite of the electric field.
And where should I draw it? Should I draw it here?
No, on the negative charge.
So now you have to go back in time when you've been taking PY105 course, and you need to imagine what's going to happen with this device if, let's say, it's attached like in the middle, just for simplicity, to a nail and can spin, and you apply at the top force to the right, and at the bottom you apply force to the left. What's going to happen?
I would think that the forces cancel out. And you're left with, yeah, I think the forces cancel out.
The net force acting on the system is always 0, no matter how we place it in the field, what's happening. The net force is always 0. It's not about net force, because it's always 0. So net force doesn't make any difference. What makes difference? The question is to you. Again.
Electric field?
No. Again, I said it's PY105. It's not PY106. You've got this device, and you simultaneously pushing to the right on the top and pushing on the bottom to the left. Take something like this. Take a pencil, place it on the table, and push it use your fingers and push it and look at it. What do you see?
It's not moving.
In that case, you're not pushing strong enough.
Oh, it rotates.
It does. It rotates. It means net torque. Have you learned about torque before?
Mm-hmm.
So that's what it is about. Net torque is not equal to zero. And net torque is responsible for rotational motion. Well, in this situation, it is clockwise torque. The direction of a torque is clockwise in this situation, in the picture. That is why it is not equilibrium. That is why it will be spinning.
I see. Okay. Okay, that makes sense.
That's PY105. And we will talk about torque in the future again, so you may kind of review it.
Yeah, my TA is gonna go over it during his office hours on Wednesday.
You got your own TA. Good.
No, my TA for this class, or my TF, sorry.
All right, more questions.
My next one is.
Let me check. How many students waiting? Oh, we've got one more student. Let's give another student a chance to ask a question as well. And then we come back. Okay, next student, next question, please. I really cannot hear you. Maybe you need to.
Okay, can you hear me now?
Now better, yeah.
Okay, sorry. I'm working a bit ahead on homework number 2. I guess I don't know how far ahead it is, but number 10 for homework part 2.
It's current, okay. Wrong. I need 106. I need homework. This one. Okay.
Mm-hmm.
And which problem?
Number 10.
It's not actually ahead. We practically, if it wasn't for technical difficulties, I would finish this today.
Okay.
All right. Let me first, what do I do? Make a copy of this. So I could see it and write. So did you check the equations for capacitors in parallel and in series?
Yeah, so let me grab those real quick again. But in series, it just adds, right? Like the distance increases. So it's 1 over.
There are 2 questions. Well,
Yeah.
actually 3. What, why, and how. So
Right.
in this situation, you're solving a problem, so it doesn't matter why. What matters is what to do and, well, how to apply it. If you have
Right.
2 capacitors connected in series, in that case, you use inverse capacitance.
Mm-hmm.
This is just something you need to remember, right?
Right.
And if you have 2 capacitors connected in parallel, the equivalent capacitance is just the sum.
Right.
This is what I will cover tomorrow right at the beginning.
Mm-hmm.
But you know that already.
Mm-hmm.
The question is now how to apply it.
Right.
If you look at this system, you need to make a statement about, well, this is C3. 3 different pairs of capacitors, C1, C2, C1, C3, C2, C3. And for each, you have to make a statement. What choices do you have? You only have 3 choices. Capacitors may be connected in parallel, in series. I don't know what symbol. There is no symbol. I need to invent. I don't know. Whatever. And neither. These are all the options. So for each of these 3 pairs, you have to make a statement.
Mm-hmm.
So C1 and C2. Can you say something about them? How?
C1 and C. Oh,
Yes, C1 and C2.
they're parallel,
Parallel.
so it'd be additive.
So you're correct. What about C1 and C3?
So they're in series.
No.
Well, with
No.
C1 and C2.
C1 and C2 are in parallel, as you said, and that is correct. But you made a very common mistake. C1 and C3 are neither.
Oh, okay.
If you could take scissors and cut this wire and remove C2, that would make C1 and C3 in series. But by adding an extra element, you break this connection into nothing. It's neither. So
Okay.
you cannot use any equation for either of these, C1, C3, or C2, C3. But you could use this. This is the only equation which makes sense. That means this is what you have to use now. And that means you can replace these two with only one. But that one must have a very specific capacitance, right? Which one? Which capacitance should it have?
It would be the sum of the.
Exactly.
Yeah.
You know that. So now you could have done it physically by physically replacing two devices with one, or you could do it mentally using your imagination. You can imagine that you have replaced two capacitors with one, but this new capacitor will have new capacitance. And this will be your new circuit. Now it is simpler because it now has only two elements. This is not the old circuit. This is a new circuit. But this is an equivalent to old one. But now this circuit tells you that with these two capacitors, you can use a rule. Which rule?
That they're in series.
Yes. Absolutely right. Which means now you can replace these two with only one, C1, 2, 3, and it must have capacitance, well, hence, which should be calculated using this rule. This is your final system equivalent to the initial system. What does it mean equivalent? It means if you apply to this system the same voltage as it's applied to this whole system, you will get the same charge distribution, the same total energy. Yes.
So how do I break that down then into the capacitors with like, so they all have the same voltage applied, right?
No.
No.
That's a different question. First of all, let's erase this. Each capacitor may have its own charge. Each capacitor may have its own voltage across. In general, but because these capacitors connected in a special way, you know that for these two capacitors, the voltage is supposed to be the same, because voltage is just potential difference between these 2 points, same voltage.
Okay.
But if you measure voltage, potential difference from here to here, the total one, I think that is given to you.
Yeah, it's on mine, it's like 1.57.
Doesn't matter.
Right.
You need to know that this total will be the sum of these two, from here to here, plus from here to here. So total will be equal to V1 plus V3, or V2, because they're the same.
Okay.
What else do you know? Well, you know that equivalent means this capacitor, which you use to replace these two, must have the same voltage and the same charge as these two. And that's what equivalent means. So you can say that this charge Q12 has to be equal to Q1 plus Q2. But the voltage should be the same as before, V1, and this is the same as before, V3. And now if you go to this, well, you have the original voltage across the whole system because it's between the same original points, A and B, A and B. Again, what is voltage? Potential difference between 2 points. So you have point A, point B. If you measure potential difference between A and B, it's always the same number, no matter which circuit you would use. It's only based on the points. But now here, this charge Q, what should it be equal to?
That's the total charge held in all three capacitors.
No.
No?
No.
Okay. It's, I mean, we can relate voltage, capacitance, and charge, right?
Of course you will, and you will have to. But you need to understand what does word equivalent means.
Oh, it's the same between, yeah.
It means that if you use this single capacitor instead of these two, this charge should be equal the same as this. When this voltage is equal to this, that's what it means. So this charge Q is actually just Q3, and actually this Q3 is actually equal to 1, 2. Because when capacitors are connected in series, the charge has to be the same. Why?
Okay.
Well, because if you connect them in series, basically what you do is you're moving electrons from one plate to another. So the charge here should be equal to the charge here times -1, but that means this charge should be equal to negative, negative, same as here, and this same as here. So in the series, they all have to have the same charge.
Okay.
You see how many connections do you have? Plus, as you just said, you can write Q1 equals C1, V1, Q2 equals C2, V2, Q3 equals C3, V3. Now Q12 equals C12, V1. Q3 equals C123, V. Did I miss anything? No, I think that's it.
So Q12 is C12 times just V1 because it's the
Yes.
same. Okay. Just double check.
Well, again, to be absolutely exact, you should have said this potential difference equals V12, but it also equals V1 because it's
Right.
because it's equivalent to original potential difference.
Okay. Thank you. I'll work on this.
Yes, and I remember from the past, because numbers are not very convenient, like very small numbers. In order to get the answers, you see, you need to keep many digits because
Okay.
people have it done correctly, but they didn't keep enough digits, and the answer was not just accurate enough for the web assignment to accept it.
Okay. Sounds good.
All right.
Thank you.
Sure. All right. All right. So still two of you. So next question, anyone?
So my next question is, if there is a charge in an electric field that does no work, can the charge still have potential energy?
A charge in electric field, let's say, always has potential energy. There is weird exception when the charge might be very, very far away, and we assume there is no electric field at infinity. And normally, we always can choose one location to be set to zero energy, because, for example, when we measure gravitational potential energy, we can choose zero anywhere we like. We could choose it here and make this energy zero. But that's a very specific location. In general, gravitational potential energy is not zero anywhere. Same with the charge. You have a charge in an electric field. Doesn't matter, positive, negative, electric field. It has potential energy equal to charge times electric potential at that location.
So what if the electric field was zero, like in a conductor that's in a static electric field?
Well, if you say electric field is zero, that means there is no electric field. That's a different situation. When the charge is in electric field, that statement means electric field is not zero.
Okay.
If you say electric field is zero, it means there is no electric field.
So then the charge would have no potential, electric potential energy.
You see, there's field and there is electric potential. You said electric field is zero. But inside the cavity, even when electric field is zero, electric potential still might not be equal to zero, and most usually is not. So force is zero when electric field is zero. Let's say electric field is zero. Force is zero. But electric potential, V, may not be zero. That means electric potential energy is also not zero, but it does not mean that if you move a charge from here to here, you do work. Because if electric potential is the same, that means potential energy inside of this cavity is not equal to zero, but is the same. That means there is no change in the potential energy when you move the charge inside the cavity. That's it.
So if potential is not zero, then
Now, what is confusing is the terminology. This letter E represents, and you need to know exactly the meaning of it, represents the electric field strength. This is the strength of the electric field. But it's a very common slang used among physicists. Call it electric field and do not say the last word, strength. So when electric field strength is zero, it doesn't mean yet the absence of electric field as a physical substance. Electric field strength is zero, but electric potential may not be zero. That means electric field is present. Only when electric field is zero, electric field strength is zero, and electric potential is zero, we say there is no electric field. Yeah, that's terminology.
so if electric field strength
Yes,
is zero,
this is
electric field strength if an electric field doesn't exist, then there's no potential and there's no potential energy.
when electric field doesn't exist in this region, there is no electric potential, well, no potential energy, no electric field strength, no force.
Okay. So in general, a charge always has potential energy.
If it is placed in the electric field.
Okay. So when we were going over the potential of an electric field, and we also talked about the potential of a point charge. When we say point charge and we use the potential equation KQ over R, do we assume that that point charge is not in an electric field?
It doesn't matter. When we say electric potential of this charge, that all that matters at this point, it will be equal to K, Q over R. Anything else is irrelevant for this statement. Of course, there might be other charges creating their own electric fields, but in that case, we would use a different name. We would have to ask, what is the net electric potential? And that would be different question, different reasoning. But this is electric potential of a point charge at the point P. That's what it is.
Okay. So my next question is for WebAssign Practice 1, question 18.
Consider this picture and well, which part, A, B, or C?
So specifically A.
A. You've got to find total electric field. For part B, that means for this picture, and you have to do what you have to do. How do you calculate net electric field? Well, net electric, yes. You see, first of all, this is again exactly the same situation which we just discussed. Language. They say find total electric field, but they say in Newton per coulomb. So they say electric field, but they mean electric field strength. That's what they mean. They just don't say this out loud.
Mm-hmm.
An electric field strength in general is equal to the sum of electric fields generated by all charges it says calculate total electric field strength for the part B at x equals 5 here. Well, you have to calculate it. Did you do this work? Did you calculate?
Yeah, so when I originally did it, I got an actual number.
You couldn't. You did something wrong?
Well, I treated it as a point as opposed to a charge, and I think that's where I went wrong.
No, it is a point. It has no size. It is located exactly where it's supposed to be. Okay, let's call them 1, 2, 3, 4. So how do you calculate the magnitude of electric field strength for the first charge at point P?
So it would be KQ over R squared, and R would be its distance from P.
Say something specific. What distance or what should I write specifically? Numerator, denominator.
So Q would be, I think it says minus 2Q. And then my denominator, my denominator would be or this is in centimeters, so 0.04 squared.
Well, you're missing magnitude, because it has to be magnitude. But besides that, yes. All right. So, and how would it point? What would be the direction?
It's going to point towards 1.
Correct.
So it'll be negative.
So this is done. Now moving on. Number 2. Tell me.
So number 2, oh, I see. So it would be minus or plus q over 0 squared. And because of that, it would approach infinity.
So the question is, why didn't you see it before?
Because I ignored the charge before.
Well, the lesson is don't ignore charges anymore.
Yes.
So all other 3 fields would be fine, but this one, the second one, gives you infinity. But this is a kind of tricky question, because no one would ask you a question like that in a real situation. In a real situation, they would ask, for example, calculate force acting on charge number 2 from other charges. And in that case, the force acting on the charge number 2 from other charges would be equal to electric field acting on charge number 2 from other charges times charge number 2. But this electric field now from other charges, and from other charges means it doesn't include its own field. There is no self-action. So in this case, you would get a nice number and you would get a nice force, of course.
Okay, I see. And then my next question is for 19A.
On the same.
Yes.
Actually, that's not what I want.
And the reason I have a question for this one is because what I did was I made Q positive and I made Q negative, and I drew out the force vectors, and from the force vectors I determined the electric field vectors.
Well, you may have done everything what you think is correct, but if your answer doesn't work, something went wrong.
Mm-hmm.
Part A. So we've got QA positive, QB positive, QC negative, QD negative. You need to calculate the direction of the force on Q.
Mm-hmm.
What is Q? Positive or negative?
So I assumed both. So I first did it with positive Q and did all the force vectors, and then I redrew the diagram and made Q negative and did all the forces again.
Well, I believe that for part A, you need to use part B. In part B, your charge is set to a specific value, and it's positive. You can't have the ambiguity. You have to make a statement.
Right. So when I
That's
made it,
So your charge Q has to be positive. If you do a different selection and the charge Q will be negative, in that case, the part A will change. But for part A, you should have only one answer. Otherwise, it wouldn't make any sense.
So there is only one answer on WebAssign, but I just didn't know if we needed to look at part B for the charge, because usually like A is irrespective of B.
Well, this example demonstrates that it's not usually. So, well, someone wrote this problem and didn't give any information. It should have said use Q from part B.
Okay, yeah, that's what I was a little confused about, because I did get the right answer if I used a positive Q, and then if I used a negative Q, it was the opposite. So it was towards the right, or the top of the page.
All of that obvious, but you can't have two answers to one question.
Mm-hmm.
You can't just, it's impossible to have on a WebAssign in this setting two answers to one question. That means you have to narrow down what's happening. That means you need to use an extra information. That extra information only comes from part B.
Mm-hmm.
So what you're saying, if I choose negative and the force switches, of course it switches. Of course it flips.
Yeah.
But it's just not the question you need to answer.
Mm-hmm. Okay. Those were, I believe, all of my questions that came up so far.
Okay. Anyone else?
I mean, if you.
Yep.
Okay. I know this is very far ahead now. Number 42 for practice part B, talking about resistors and stuff.
It's actually very, very similar to capacitors. So
yeah, and that's what I noticed.
I just want to.
Yeah.
Where is it? Too many windows. Part B.
Part B, number 42.
You're really far ahead.
I try. So
38, 39, 42. Okay.
Yeah. So I understood everything up to this part, with resistors in parallel and in series. But I was a bit confused about having like two batteries.
Yes, it is slightly confusing. So in general, a battery is just a source of a fixed potential difference.
Right.
And every battery has a low potential terminal, negative, usually we call it, and a high potential. And we could always, electric potential V, it is related to potential energy.
Mm-hmm.
And again, as we know from our previous experience, for example, when we measure gravitational potential energy, we can always choose from what level. We can always choose where the energy is zero. We choose it. And then we measure relative to this point.
Right.
Same we could do for electricity, for any circuit. We can choose one point, let's say this one, to be zero potential. And now relative to this point, all other points have a potential, maybe positive, maybe negative. For example, this point will be higher by this value.
Mm-hmm.
Do you know it? I don't see it.
I mean, on my example, it's 7 volts. I think all of the,
Oh, okay, they're all the same.
yeah.
Okay, so in your example, it's 7. All right, we can make it 7. So if this electric potential is set to 0, this automatically will be 7 plus 0 because the battery increases potential by this value.
Mhm.
Now, did you find the electric current already? No?
For the whole system, no. I was a bit confused at
Well,
as
any
to how
electric
they
current. All right, doesn't matter. So now what we do is we analyze how electric current will travel. Again, let's start from this point because we set it kind of to the origin.
Mhm.
So we assume, well, electric current I travels outside of the battery, travels from higher potential to lower, like skiing down the hill. So it will travel this way, then it will travel this way, then it will travel this way. I don't know, let's call it I1. Here it should split between I2 and I3. And I3 travels and travels, and here at this point, we call it junction, it combines again into original current I1, but it doesn't stop here, it keeps traveling, and now, so this is what's happening.
Mhm.
So you probably read already about the Ohm's law, right?
Right.
So the Ohm's law relates electric current, resistance, and potential difference.
Mhm.
So if you have a resistor R, and if you have electric current I traveling through it, in that case, there has to be potential difference between these two terminals, electrodes. Because if potential difference would have been 0, electric current would have been 0. There would not be current. And we also know, I will talk about probably on Wednesday and Thursday, that electric current travels, not electrons. Electrons actually move in opposite direction. But those kind of fictional positive charges, people used to imagine that positive charges have been traveling inside. They didn't know about electrons.
Mhm.
So those positive charges would be traveling in the direction of electric field from high potential to low potential. High, low, well, high, low. So this difference will be equal to difference, actual mathematical difference between two numbers. So this is how electric potential changes in the direction of a current it drops.
Right.
So for example, here, so let's call it V1. This electric potential will be equal to 7 because battery rises it from 0 to 7.
Mhm.
But this electric potential will be lower. V2 will be lower by what value?
By the current times the resistance.
Yes, but we need to keep track of what current, what resistance.
Right.
So now we go further. This point, electric potential here. Well, electric potential here should be higher than number 2 by the battery, because battery again brings it up by this value.
Mhm.
All right. Now let's go to potential number 4 right here. And for this potential, we can use two different branches of this circuit. We can look at this part, or we could look at this part.
Mhm.
And for each, we could write an equation. Again, what is happening to potential number 4? Well, it should be lower than potential number 3 by what? On one hand, it should be lowered by this current times this resistance. On another hand, it should be lowered by this current times that resistance. That's how law works. It is exactly the same law again and again and again. And this potential 4, actually has to be equal to 0 because nothing else is there. So it's
Okay.
it's the same final potential. Well, now it's final, but it also was initial. It's the same potential. So now, now you've got so many different equations, and you can solve all these equations to calculate electric current number 1, number 2, number 3. And if you know electric current, you can calculate power, because for that you just have to apply an equation for the power. So how much power batteries deliver? So it should be power number 1 plus power number 2, totally. And well, they share electric current, so it has to be same electric current 1 times power times first EMF, and same current times second EMF. That's it.
Oh, I'm sorry, I can't see the edge of your screen.
It's blurry?
No, it's a bit cut off.
Which part?
The last equation, I just see current times battery 1. So I don't. Okay.
Do you see it now in full?
No, almost.
Well, I can move a little bit more.
Yeah.
Just need to align.
Okay, perfect. Yes, that's good.
So for like any element with a given potential difference in electric current, the power dissipating equals this.
Right.
You could use Ohm's law if you want to calculate the power for resistance, but you know, for the battery, because we assume that the battery is ideal, it has no resistance. You cannot use Ohm's law for the battery. You just use this.
So how again do I find the total current, or just current 1?
Well, the word total might be tricky.
Yeah.
In general, you should say electric current traveling through, then point your finger and say this element.
Okay.
Electric current traveling through first battery, that's I1.
Yeah.
But it's the same as electric current traveling through first resistor or electric current traveling through the second battery. It's all the same. There's one more equation I didn't write. I said it, I didn't write it. Here or there, when electric current splits or electric current combines again, you have to write that the total amount of it before and after is the same. So this is another equation. So you've got 1, 2, 3, 4, 5, 6, kind of 7 equations.
Right. Okay.
Physics is done. Now you need to start manipulating with these variables. And the easiest way is to rewrite it in terms of potential differences. For example, V4 minus V3. It has to be equal to this from this equation. However, it also has to be equal to this from that equation. See? And
oh, I'm sorry. What are the subscripts? It's a bit blurry.
3, 3, 2, 2.
Okay.
So what you know are resistances, right? You know resistance number 1, number 2, number 3, and what do you know? EMF. Okay, so if you know EMF, that will give you this difference, which is, where is it? 2 minus 3. What would be the easiest way to do it? So if I wanna take a look at the loop. I wanna make it. So one more equation, and mathematics. I2 is here, and eventually I want to get to V3 minus V4, right? So this is one equation. Now what can I do mathematically? I don't want to use anything else but Ohm's law, although we could.
So the equation you wrote was, it might not be visible on my screen.
By some reason, oh, this what I'm looking for. This what I'm looking for. This one, equation number 1. So,
Okay.
So, because in this equation I've got numbers.
Right. And we know V1 equals 7 volts.
So V2 equals 7 minus I1 times.
And the resistor value.
I don't know your value.
7.1 ohms.
All right, 7.1. 7.1. So now this could be used here to eliminate this. Basically, you just have to do the elimination procedure until you get only one unknown.
Right.
So this gives you V3 equals 7 minus I1 times 7.1 plus, again, 7. Now, so now what I want to do, I want to get rid of V4. So I'm going to actually
Well, we know that equals 0, right?
Oh, you're right. I didn't use that. V4 has to be equal to 0. So that's equal to 0. This is equal to 0. So I can write that V3 equals I3 times R3, and that is equal to 7 minus current number 1. Well, 7 plus 7, 14. Okay, 14. So we're getting closer. Because now I've got an equation with 2 unknowns, but I also can relate these currents. For example, see what I can do. I can replace I1 with the sum of 2 and 3, and I can replace, so this is going to be my equation, I3 times R3 equals 14 minus I2 plus I3 times 7.1, right?
Right.
But now you could replace I2 with I3 again, or I3 with I2 again, doesn't matter. If you use this equation, this equation, you can eliminate I2, and that will give you final equation with only one unknown, I3.
Okay.
And when you solve this equation, everything else automatically falls into places, because if you know current number 3, you can calculate current number 2, and then you can calculate current number 1. That's it.
Right. Okay. Perfect. I will work on that on my own.
I just want to
And-
say that there are so-called Kirchhoff's rules. I just want to say that we don't learn those rules because they're identical to this. They would just give a final equation faster.
Mhm.
So it's just in case,
Okay.
But the Ohm's law always eventually, plus this junction rule, always eventually can be used to derive an equation with only one unknown and solve it, and then done.
All right. Thank you so much.
Whew. Thank you.
Take care. Bye.
Have a nice day.
You
Bye.
too.